In this section, we're going to talk about permutations and combinations. First, we want to define factorials. So in factorial, for any natural number n, is denoted by n with an exclamation mark. And what that means to do is to take that number multiplied by every number below it. And then 0 factorial wouldn't really have much of a meaning in that sense because it doesn't have any numbers below it, but it's defined as 1. So anytime you have a 0 factorial, that's just 1. And for all the other ones, you will multiply that value by every value below it. So let's practice evaluating some factorials. The first one says 5 factorial over 2 factorial. So what this would mean is to take 5 times 4 times 3 times 2 times 1. That's what 5 factorial means to do. And divide that by 2 times 1. The easiest way to do these is to just cancel out the like factors. And so it looks like on this one we end up with just 5 times 4 times 3, which is 20 times 3, which is 60. Okay, what about something like 6 factorial, 3 factorial, all divided by 4 factorial? So this would mean to do 6 times 5 times 4 times 3 times 2 times 1 times 3 times 2 times 1 all over 4 times 3 times 2 times 1. So let's see, these 1's cancel, 2's and 3's, and then this 4 could cancel with that 4. So we would be left to take 6 times 5 times 3 times 2 times 1 over 1 because everything on the denominator canceled. So that gives us 6 times 5 times 3 times 2 times 1, 180. This one's going to be kind of long. Let's see, 11 factorial. I hope I have room to write it here. 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 all over 8 times 8 factorial, which is 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 times 3 factorial, which is 3 times 2 times 1. Okay, start canceling things out. I'm going to start with these. Let's see, we've got a 1's at the end, 2's at the end, 3's at the end. Okay. Let's see, we've got 8's, 7's, 6, 5's, and 4's. So it looks like we've got an 11 times 10 times 9 left on top and a 3 times 2 times 1 on the bottom. We could multiply this out, or we could do a little bit more canceling. The 10 and the 2 could cancel to a 5 and a 1, and the 9 and the 3 could be a 1 and a 3. So it looks like on the top we have 11 times 5 times 3 over 1. So we just need to figure out the 11 times 5 is 55 times 3 is 165. Now there is a button on your calculator that does factorials, but it's sort of hidden to the fact where if I'm doing multiple factorials at a time, I would rather personally just do it by hand. However, there is a way to get to it. So for instance, if I wanted to just do, let's say 5 factorial, I could go 5, and then you have to go into your math and over to probability, and it's number 4 under there. And it will calculate that 5 times 4 times 3 times 2 times 1 for you. But again, if you're doing several of them, I personally find it more cumbersome to do this than to just write it all out and do it sort of by hand. But you can do it either way you prefer. Okay, that leads us into what permutations actually are. So a permutation is if you are given a set of distinct objects, and that distinct is important, so you can tell them apart. Then a permutation of this set is an arrangement of these objects in a definite order. So those are the two key pieces. To be a permutation, you can tell the objects apart, and order matters. If either one of those things is not there, then it's not a permutation. Anytime you're asked to determine the number of ways an object in a set can be arranged in a line, Order is important, right? Because what comes first, second, third in a line matters. The order matters. Ask any child whether being first or second in line matters. It does. Okay, so for our first example, we're going to do how many different orderings are there for the letters A, B, and C? And we're going to first do this by drawing a tree diagram. So we are ordering them. Order matters. So this is a permutation. I can tell the number or the letters A, B, and C apart from each other, so it checks both qualities. Okay, if I'm going to put these in a line, I have 3 choices for which one's going to be first in line. Either A or B or C will be first in line. So for my first, I have 3 choices. Now, because you can tell these objects apart and that letter is now first in line, we only have 2 options for what comes next. These are sort of the without repeating type situations. Once I've used one of these letters, I can't use it again. So after the A, I could either put B or C. If I chose B first, I could either do A or C. And if I chose C first, I could either do A or B next. So at each level, though, once I've chosen the first one, there are 2 choices for the second one, right? Once I've chosen this one, on my next level, I only have 2 choices each. At that point, I've basically exhausted all my options. There's only 1 choice each in the last one, because if I've chosen A already and B already, then the only thing left is C. And I can fill the rest of this in. A and C leads to B being last. B, A leads to C being last. B, C leads to A being last. C, A leads to B being last. And C, B leads to A being last. So there really is no choice at that point. There's a default who has to be last. So how many different orderings are there? There are 3 times 2 times 1, which is 6 different orderings. And again, we could write those out. There's ABC, ACB, BAC, BCA, CAB, and CBA. And this is a good way to do it, to actually write them all out, because if you, in a very structured way, because if you just try to think about them all on your own without writing them out in a specific order, chances are you're going to forget or just miss at least one of those. Okay, what about if 5 chairs are placed in a row? How many different seatings, or how many different ways are there to seat 5 people? Anytime you're doing something with people, you can tell them apart, so your order is going to matter on those. So we would have 5 choices for the first seat, 4 for the second, 3, and then 2, and then 1. If I take 5 times 4 times 3 times 2 times 1, that's 5 factorial, which we actually just did. We know that's 120. You have 3 math books, 4 history books, and 5 English books. In how many ways can these 12 books be arranged on a shelf? Okay, so you have 12 total books, and I'm assuming they're all different books. It seems as though they are. So you can tell them apart, and you want to arrange them on a shelf. So in this case, order again is going to matter. Anytime you're arranging things, order matters. So this does count as a permutation. We've got 12 different books. So we would have 12 choices for the first, 11, then 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, which is 12 factorial, which is, now here's a good reason to use that factorial button in my opinion. I'm only doing one of them. Instead of typing all of that into my calculator, I can just say 12 factorial. So again, I'm going to copy these digits down and then put in my commas so that I can figure out how to say this. Okay, so that's 479,001,600 ways to put those 12 books on a shelf. So what this leads us to is this permutation rule, which is that the number of permutations of indistinct objects taken in at a time can be denoted in two different ways, depending on, or there's probably more than this as well, but these are the two most common ways you'll see this maybe in online videos and in textbooks. So it's either P in comma in or in P in. So this means I'm going to take this many objects and I'm going to put them all in a row. And this can be defined by taking in factorial. So that's what we've been doing. What happened up here was we permutated 5 objects 5 at a time, and that ended up giving us 5 factorial. And in this one, we permutated 12 objects 12 at a time, and that ended up being 12 factorial. Okay, so what if we want to do a slightly more difficult problem? This one says we take those same 3 math, 4 history, and 5 English books. This time we want to arrange these 12 books on a shelf, but we want to keep the same subjects together. That makes sense. Okay, so to arrange the math books, we want to permutate. There are 3 math books and we want to put all 3 of them on a shelf. So we know that that's 3 factorial. Then we would like to arrange the history books. So we have 4 history books and we want to take all 4 of them and see how many arrangements could we make of just the history books. That would be 4 factorial. We want to arrange the English books. We have 5 of them, and we want to put all 5 of them in every order that we could possibly get to, so that would be 5 factorial. And then the last thing you want to do is arrange the types. So there are 3 different types of books. Do we want to do math, then history, then English? Or do we want to do math, then English, then history? So if we want to arrange the types, we again have to permutate 3 different types. So 3 factorial. 3 factorial is just 3 times 2 times 1, which is 6. Again, we're multiplying. This is that same rule. 4 factorial is 4 times 3 times 2 times 1, which is 24, times 5 factorial we've already done in this sheet, which is 120, and then another 6. So if we multiply all these out, we get 103,680 ways. So notice how different that is from earlier, when we just wanted to put them all in a row and it didn't matter if the math, history, and English were kind of intermixed, how many options there were there, and then how many, if we want to keep the different subjects together, how that drastically cut those permutations down.